if you look at your continuity equation, and let us say you write it like this, and then you integrate the two sides in y. Okay, say you integrate it to some y. Okay, then what you are going to get is v of y minus v of 0, which is basically 0. Okay, so this guy is 0 equals minus of del by del x u dy. Okay, and over here what we can do is we can write this as minus del by del x of u dy. So I can do a plus minus of u infinity dy. Okay, so all of these quantities are dimensional so far. Okay, I'm dealing with dimensional quantities. All of these are dimensional. Okay, of course this guy delta hat would be dimensionless, because no, it actually won't be dimensionless. You have dy here. So okay, let us say we write something like this, and then what we are, so what is interesting to notice here is that this is minus del by, or rather del by del x of integral 0 to y u infinity, and so there is a minus outside, so there is a u infinity from here, so u infinity minus u dy, and then a minus of 0 to y u infinity dy. Okay, now for a minute look at it for a flat plate. So for flat plate and also 0 pressure gradient. So when you have 0 pressure gradient, and for a flat plate. Okay, basically we are looking at the special case when this u infinity is constant. Okay, we are looking at the case where u infinity is a constant. Okay, so when u infinity is a constant, I can pull this u infinity out of the integral. Okay, I can basically pull this u infinity out of the integral. So let us just simplify this, or we may not need to do that. Let's see. So now let me take this del by del x inside and look at this quantity. So this is del by del x of u infinity times 0 to y 1 minus u by u infinity dy minus del by del x of u infinity 0 to y dy. Okay, this is what we have for v of y. So we are basically looking at what is the y direction velocity, and what does this y directional velocity actually mean. We will come to that in a minute. Okay, so for this, when u infinity is a constant, this guy is 0. Okay, du infinity by dx is 0. Okay, and if I am integrating it to any particular y on an x station, that does not matter. So this term will basically be 0. Okay, or if you want to not substitute that here, what we can further simplify this as v of y is going to be minus of d u infinity over dx times y plus del by del x of u infinity. Now if you look at this quantity 1 minus u by u infinity dy, this is basically that delta hat. Okay, now look at this expression for a minute and let us think about it intuitively. What does this v of y equals this mean? So if you look at this term minus du infinity by dx times y, what is basically this trying to tell you is that if there is a gradient of u infinity in x direction, if u infinity is changing in x direction, then you will have some y direction velocity. So, let us say this y direction velocity due to that change in x of u infinity, and that is mandated by your continuity equation. Okay, continuity equation is always satisfied. So, this is basically that term that if you have u infinity varying in x, that results in a bidirection velocity, because if du by dx is not 0, then dv dy is not 0. There has to be some changes in y. Even if v is 0 at some y, it does not mean it is 0 everywhere. Okay, that is the main important point from this term. What does this term mean? What is this term trying to tell you? So, now let us look at the special case of, so special case of flat plates, and basically we are saying that in that special case where du infinity dx is 0 and u infinity is a constant, we are saying v of y is simply u infinity d delta hat over dx. If you go back to your lubrication approximation, when we were looking at flow inside these kind of channels with varying height, then we had said that the y direction velocity scale, we had derived that it is x direction velocity scale times h over L. How the y direction surface in y direction is changing in x, okay, something like dy by dx, which makes sense also when you have a flow that is being turned by the walls, okay, whatever the tangent of the walls is, it's basically that those walls are trying to direct the flow in that tangent. So, if you have a flow that has speed u infinity and you are trying to turn it, then your x direction velocity is u infinity cos theta, y direction is u infinity sin theta, and so on and so forth. So, you are basically writing this by saying that this is tan theta, okay, which makes sense also, but over a very large distance you are saying that. Okay, this is your v, this is your u, this is that theta. And now compare that with this expression. In special case of flat plates, you have a v of y which is u infinity d delta hat over dx. Basically what it is trying to tell you is that even if you have a flat plate, when you have, let us say, a flat plate and you have a flow grazing past this flat plate, let us say you are sitting here, you do not see 0 y velocity, you see some y velocity which is due to the presence of flat plate, and that flat plate, basically you imagine a flow that is hitting this flat plate and getting curved ever so slightly. Okay. The important point here is that that curvature is not d delta over dx, where delta is the boundary layer thickness, is d delta hat over dx. Okay, that, yeah. No, this is outside the boundary layer. There is nothing inside the boundary layer that I have used so far. Okay. So, by the way, this is so d delta hat. This becomes delta hat only. Yeah, this becomes delta hat only when y is tending to infinity. By the way. Okay, this is a limit that we are evaluating, because this quantity 0 to y 1 minus u by u infinity is technically delta hat only when this upper limit is infinity. Okay. So, we are evaluating this at the limit. So, I am telling you that very far away from the plate, there is a y direction velocity which is equal to this. Okay. And now if you go back to our scaling analysis, you will see that this this y direction velocity is actually small. Okay. The scaling of this y direction velocity is actually 1 by square root of REL times this u infinity, where REL is much greater than 1. So, the y direction velocity is small, but it is not 0, and that is the important point, and that is the physical intuition behind delta hat, the displacement thickness. In a way, what we are trying to say is, let us say you integrate, this is height h which is greater than the boundary layer thickness, and you integrate your mass flow rate here. Okay, let us say you integrate the mass flow rate here. So here it is u infinity times h, and here it is, let us say, u dy 0 to h, and you have u infinity h. So whatever flow is coming from here, the flow that is leaving here is not going to be equal. There will be some outflow from this control volume in the y direction. Okay, and how do you calculate that outflow? It is through this. Okay, it is through this. And there is another thing that we can say, that let us say, let us imagine a hypothetical case where, let us imagine a hypothetical case where we could ignore the boundary layer completely. Okay, and instead of h, let's say this was some delta hat, and this is your h. So this is your control volume, by the way. Okay, and so what I'm saying is, so this is not equal to this, but if you did the integration of u infinity times h minus delta hat, okay, and you calculated, so what is delta hat? Let's say this delta hat is this, I substitute, this becomes u infinity h minus 0 to infinity 1 minus u by u infinity dy. Okay, let us look at what this quantity gives us. And this is basically u infinity h minus, so this quantity, if you look at, we say that u of y equals delta is becoming u infinity, where this is the boundary layer thickness. So you can also write it as 0 to delta u infinity minus u dy. Okay, the reason why I'm covering this aspect is because this is how boundary layers were solved practically uh, before numerical solutions of Blasius equation could be done. Okay, this is called von Karman Paulhausen method. I don't know if you, I mean, based on this, that method is derived. You can look at this method in the textbook. Okay, the it's not a very a very used method these days, but back in the day it was used, and even today you can try using it to get some good designs of aerodynamic shapes. Okay, the momentum integral method basically. And from here what you can get an intuition is that this u infinity h minus delta hat is basically this u infinity h minus, so this quantity is basically this u infinity delta hat, and what you are trying to say is that the flow here and the flow here, you can look at this derivation in the textbook. I'm not going to do that here. If you assume that your flat plate is shifted by this delta hat, then the flow rate on the left side and right side will be same, and it will be equal to whatever flow rate you have here. So this flow rate is u dy 0 to h. Okay, and this flow rate will be u infinity h minus delta hat, and you can prove that these guys will be equal. Okay, if you just simply ignore that there is a boundary layer. So in a way, this delta hat is indeed the displacement thickness. What it means is that if I raise my delta, let's say you have this kind of a flow in a duct. So you have two flat plates. Okay, you have two flat plates over which you have boundary layer. Okay, now someone asks you, okay, what is the flow rate inside if I am giving you if I don't give you some velocity or something? What you will say is, okay, I displace this flat plate by delta hat, I displace this by delta hat, and I calculate the flow rate assuming inviscid flow. Okay, that is the intuition behind this delta hat and why it is called a displacement thickness. Basically, it is the thickness by which you can displace your boundary and forget about the boundary layer. Okay, to compute the flow rate. So this u dy you can show is equal to this. Okay. So this you can show is going to be q dy 0 to h. Okay. Now moving forward, we have discussed our boundary layer separation. I just wanted to give some names which are called to those regimes that we were discussing. So if you recall, before the demonstration we had discussed this case. Okay, we had discussed, I had made a diagram of it over a curved surface, and we had said that if your dp dx is less than 0, then you have a dp dx equals mu del to u by del y square at wall, because at wall we had u and v equal 0. So you can substitute this u and v equal to 0 in the boundary layer equation. So what this means is that del to u by del y square at wall is less than 0. So what it means is that the gradient del u by del y is decreasing. As you move up, the gradient del u by del y is decreasing. Since this is a boundary layer, del u by del y has to go to 0 at the boundary layer thickness, because outside boundary layer there is no u as a function of y, okay, for at least flat plates. So del u by del y you are saying is decreasing and it has to go to 0. It is continued monotonically decreasing, you will see. Okay, at wall it is less than 0 and over above it is also less than 0. So it is monotonically decreasing. Okay, so it will start with a very high positive quantity del u by del y and it will slowly go to 0. So if you plot it del u by del y, it will look something like this. Okay, notice that I haven't made, so this will be del u by, this is how del u by del y will look like. Okay, and notice I have not made it like this here. Okay, I have not made the gradient of del u by del y 0. That occurs when your dp dx is 0. Okay, that occurs when your dp dx is 0. And if you have a case where you have pressure gradient that is less than 0 and then a pressure gradient that is greater than 0, what happens is, as you transition from less than 0 to greater than 0 points, you will have del to u by del y square transitioning from less than 0 to greater than 0 at wall. Okay, and what it means is that if del to u by del y square is greater than 0 at the wall, that means your del u by del y will increase from the wall and then decrease. So if you made a plot of del u by del y here, how will it look like? How will the plot of del u by del y look like for this kind of a case? Let's say this is your u versus y. How will del u by del y look like? How will del u by del y look like? How will del u by del y look like? So here del u by del y was decreasing monotonically. Here you will have del u by del y that won't decrease monotonically. Okay, first it will increase. So if you have this kind of a case, then del u by del y is negative here, right? Velocity is increasing in the negative direction as you move up in y. So del u by del y is something like this, and then you have this kind of a case for del u by del y. There is a point where del u by del y is 0. Technically that should be somewhere here, and there is a point where del u by del y has a maximum. Okay, where del u by del y is maximum. So del to u by del y square is going to be 0 here, and these kind of points are called what? Inflection points. So there is an inflection point that you have here, and in this case where you are going from dp dx less than 0 to greater than 0, you have inflection point at the wall, because at the wall where your dp dx is 0, you have del to u by del y square. You have del to u by del y square equals 0. So, in this kind of a case, this region will be called a region of favorable pressure gradient. So, favorable means favorable to the boundary layer. Okay. The word favorable means the pressure gradient is favorable to the boundary layer. It maintains the boundary layer. Here, this is called an adverse pressure gradient. Okay, this is called an adverse pressure gradient. Okay, and you can relate. You have actually seen this kind of a phenomena in your undergraduate fluid mechanics courses, where let us say you were discussing about the venturi meter. Okay, you know that when you looked at venturi meter, you have flow that is coming here, and then you have some region where you have the minimum area, that is called the vena contracta, and you were said that, oh, there are circulation regions here. What do those circulation regions mean? Basically, what is happening is that the boundary layer has separated. Why is the boundary layer separating? Because after the contraction, when you have a diffuser region, the pressure is increasing. The pressure is increasing here. dP dx is greater than 0. Okay, pressure was increasing as you moved downstream. Here dP dx was less than 0. Here dP dx was less than 0. So, this region is favorable to the boundary layer. Basically, it tries to maintain the boundary layer, and there are ways in which you can induce this pressure gradient which is negative enough so that it suppresses the boundary layers enough. Okay, basically suppressing means it will make it thinner and thinner and thinner. Okay, and I would like to connect this to the wind tunnel model that I showed in the previous class. If you remember, there was a region, there was an inlet here. Okay, there was an inlet here, and then you have a region, something happening, and then there was a contraction zone here, and here we were doing the flow visualization. This contraction region is introducing a favorable pressure gradient. So, it is trying to maintain the boundary layer. Why is it important to maintain the boundary layer? Because I do not want any recirculation zone in my test section. I want to model the flow as it is coming as a uniform flow past some object. So, I want to maximize the area where in area in the test section where the flow is uniform, and that is why we have a contraction zone in all of wind tunnels. Most of the wind tunnels, as you would see wherever you go, you will see that there is a contraction zone upstream of the test section. And the reason to do that is because you want your boundary layer not to separate. You do not want these circulation zones coming into picture. You do not want adverse pressure gradient. Okay. Any questions so far? So, you can show that u infinity h minus delta hat is going to be equal to this u dy 0 to, let us say, h. As long as your h is outside boundary layer, you can show this is going to be the case. Okay. For that, what you will have to do is write this 1 minus u by u infinity, and so 1 minus u by u infinity dy technically up to infinity is equal to 0 to delta, right, because after delta u is equal to u infinity, this quantity is 0. Okay. So, you can show once you substitute this delta hat, and you can show that this is what you will get. Okay. The idea is that displacement thickness is trying to account for the presence of boundary layer, okay, in changing the flow rate across this control volume of height h. If you have a control volume of height h, you have a flow rate coming out, okay, of this section. It is not equal to u naught u infinity h, because there is a flow rate up. So, this is something less than u infinity h. How much less? It is actually less by u infinity delta hat, u infinity times delta hat. Okay, you can show this, do this calculation. And so you have a favorable pressure gradient and an adverse pressure gradient where you can have flow separation. And if your until unless your experiment is about modeling adverse pressure gradient boundary layers, okay, you don't want flow separation to happen. So I don't think we should cover 3D boundary layers. There is not enough time in this course. So in the textbook, you can look at other types of boundary layers and how to solve those also. For example, there are 3D boundary layers that are given in the textbook, and there are uh, boundary layers over axisymmetric bodies that are given. Okay, how to solve them? There are particular transformations which you can do to solve them. So we will close the boundary layers here, but we will not close the boundary layer theory here, because the next thing that we are going to look at, and it is very important, are 2D jets. Okay, and the problem goes something like this. So you have a uniform flow of, let us say, speed u naught coming out of an orifice which has a height, let's say, h. Okay, and so I'm going to put my coordinates here. I'm going to put my coordinates at the exactly at the outlet of this orifice, and so at the orifice you have this type of a flow profile right at x equal to 0, and then as you move further downstream, your flow profile tends to become something like so, something like this, and then something like this. So maybe if we were to track the point where the flow is not there or the flow velocity is becoming 0, then we would probably get something like this. Okay. And now the idea is that boundary layer approximation that we have made. What was the boundary layer approximation? If you have this as some delta, if you have this as some L, and let us say you have an REL, which is, in this case, it's going to be u naught L over nu, then we said that this REL is much greater than 1. Okay, and you have delta over L equals 1 by square root REL. Under this approximation, we had derived our conditions, we had derived our equations, del P star over del Y star equals 0, and U star del U star over del X star plus V star del U star over del Y star equals minus del P star over del X star plus del 2 U star. And of course, we have the continuity equation. Okay, this is the boundary layer approximation. This is the boundary layer approximation, and we can assume this boundary layer approximation to be valid in not just boundary layers. This boundary layer theory is applicable whenever you are looking at a flow that is sufficiently far away from some kind of an inlet, but it is developing in both x and y. It is not any fully developed flow, so there is a change of flow in x, but the idea is that the change of flow in x is very slow compared to the change of flow in y. As you move equal amount in x, you may not see some amount of change in the flow, but if you move equal amount in y, you will see a very large amount of change in the flow. So the idea of boundary layer approximation is, intuitively, it's that the change in x direction is very small compared to the change in y direction. okay, and that is basically something that you can apply in jets also, especially when you are sufficiently far away from the inlet. When you are sufficiently far away from the inlet, you can apply that this boundary layer approximation. Now, one thing that I want to ask you is, let us say I make a control volume like this. Okay, this is my control volume. Okay, this dashed square that I have made, let us say this is my control volume. First of all, what happens to the pressure along this line? What can we say about pressure along this line? What you see here? Why? So, huh? Bernoulli is out of the class. Okay, Bernoulli is not here anymore, and we don't overuse it. We are in the viscous regime. We are not saying pressure Bernoulli is applicable. Outside it may be, but then outside you don't have any variation in velocity. So del P star by del Y star, if we are sufficiently far away from inlet, okay. So this control volume is all the way up to here. We are sufficiently far away from the inlet. We have del P star over del Y star equals 0. So if you have atmospheric pressure here, if you have a jet coming out in the atmosphere, basically the pressure throughout this jet you can assume to be equal to some P infinity, okay, because pressure here is not changing. In x direction pressure is not changing outside the jet. You are saying that within the jet pressure is not allowed to change in y direction, so the pressure is going to be constant. Okay, the pressure is going to be constant, and this is also a reason why these are called free jets. Basically jets are coming out in a free atmosphere. Okay, you don't have any pressure gradient outside in the jet, and so you assume that pressure is constant everywhere. So del P star by del Y star is 0. This means P star is some function of x, but P star outside jet equal to P infinity star, let's say, which is constant. That means Fx is P infinity star, which is constant. This is a very crude approximation. Okay, I'm not going to go into detail what happens in this region. There will be some dp dx here that you will see. We are going to ignore that, and we are going to assume that pressure over all of this boundary and over all of this boundary is same, and it is equal to this P infinity star. And what is this P infinity star going to be? P infinity star is basically your P infinity over rho u naught square. Okay, it's a non-dimensional quantity. Yeah. So you're right, boundary layer theory was applied for boundary layers, but here what we are saying is that you can think about the boundary to be, let us say, this boundary which has some flow. Okay, the boundary the x axis is the boundary which has a flow, and you have it above x and below x. The fluid is extending to infinity, and that has some velocity. Okay, the idea here is that boundary layer theory was first applied to boundary layers where you have a wall and stuff like that, but the approximation of boundary layer theory is actually applicable at in other places also, because boundary layer, when you made that boundary layer theory for walls, you made an approximation which you can actually practically reproduce in other cases as well without any particular boundary. Okay. Here you have a flow that is coming out of that orifice into the free atmosphere, and sufficiently far away from that orifice also you can say, oh, my flow is not going to vary too much in x, but it is going to vary faster in y than x. Okay. So you are right to question this, and in practice actually these kind of free jets are jets in very jets at very small velocity. So for example, you guys may have seen that submerged jet experiment in your fluid mechanics lab. That is certainly not an example of a free jet. That is a very high pressure thing that is coming, and you have to move very sufficiently far away from that orifice to reach this region. And even then we are going to look at laminar jets. In that case you don't have a laminar jet, plus there is gravity which is acting in this direction in that particular case. So this is a very non-intuitive application of boundary layer theory, but nonetheless it works. So velocity where is small?
Just now you said that the velocity is not too large.
So velocity here is not too large, where velocity here is sufficiently large, and we are saying this approximation, we are working under this approximation, that whatever velocity you have here, if your u naught L by nu, okay, is sufficiently larger than 1, and for any small velocity you can make this condition valid by moving far away, by moving sufficiently far away. Okay, by moving sufficiently far away you can make this condition always valid. It is actually more about this condition than this. Okay, this can always be satisfied. It is more about this condition. Boundary layer approximation is a combination of these two. It's not just high Reynolds number, it's a combination of these two, and that's what I'm trying to say, that we can actually apply this, the combination of these two, which are the boundary layer approximations, in seemingly unrelated flows as well. Okay. And so what we are saying is that, you had a question? Yeah, go ahead.
How did we conclude that pressure inside the jet is constant? I did not understand.
So if you are inside this jet, let's say you move outside the jet at a particular x location, you're not going to see any change in pressure, right? So outside the jet you have P infinity. So that means inside the jet also it was P infinity. And you can do this at all x locations and conclude that pressure is P infinity at all x locations. Yeah, go ahead. Hmm. Huh? Okay. But pressure head and kinetic head, these are these are Bernoulli concepts, right? The Bernoulli theorem concepts. Bernoulli theorem doesn't apply here. Bernoulli's equation doesn't apply here. Pressure head, kinetic head. If you're probably you were saying pressure head is constant, why is velocity head not constant? Because Bernoulli equation doesn't apply here. Bernoulli equation applies outside your jet, but not inside the jet. You cannot move inside the jet and still expect that P plus half rho u square is constant. Okay. So this is there, that pressure is constant. So that means we get our equation. So again, I'm going to drop the stars, by the way. And then we have this. And then we have this. So interestingly, at least the governing equations, not worrying about the boundary conditions so far, the governing equations are the same as zero pressure gradient flat plate boundary layer. The governing equations are same as zero pressure gradient flat plate boundary layer. But as you will see in a moment that the solution is not, you don't apply Blas's equation here because the solution is actually very different because the boundary conditions are different. Okay, and we will get to the boundary conditions in a minute, but first what I wanted to ask you is, again consider this control volume, okay, and let us apply the mass equation or the continuity equation across this control volume. So, we have del u by del x plus del v by del y, which is equal to 0. Let us integrate this over the control volume. Okay, that is what we are doing. The continuity equation we are integrating over the control volume. Okay, our velocity scales are something like this, by the way, and we can take a y scale, which is, let us say, h here. Okay, this y scale is given, and so you can think of that v scale is going to be u naught h over L, and we are in the zone when h by L is equal to 1 by square root of REL. Okay. So, this should also tell you that boundary layer approximation in free jets basically means that your Reynolds number is high enough and h by L is, hold on, yeah, h by L is small enough, which means if your diameter or the height of this orifice is some 1 centimeter, then you are greater, much greater than 1 centimeter away from this orifice. That is what this approximation results in. Okay. So, this should tell you that all of the analysis that we are going to do is sufficiently far away from the orifice. Okay. All of this analysis is sufficient. So, let us do this integration over the control volume that we have. We know del u by del x plus del v by del y is 0. So, I can always integrate it and still make it 0. Okay. So, what do we get here? So, this is del u by del x dx dy, right. So, let us say this is x equal to 0, this is some x equal to capital L, okay, all in dimensionless because I am dropping the stars. Okay. After this point, everything without stars is also dimensionless. So, this basically becomes u at x equal to L minus u at x equal to 0, this integrated in dy. Okay. And let us say this is minus of some capital H, so to plus of some capital H. So, the units are something like this. Okay. And this is what you have, u of x equal to L dy minus h to h. What is u at x equal to 0? It is just u naught from, let us say, minus h by 2 to h by 2, and it is 0 everywhere. Okay. So, that integration is actually very easy because we have minus half to plus half and u naught, which is basically 1 when you non dimensionalize. So, this is what we have. Okay. All of these are dimensionless quantities. Please convince yourself that this is what you will get when you have non dimensionalized with these scales. Okay. And this quantity is basically 1 minus h Okay, this is what we get when we integrated del u by del x term. Let us do an integration of del v by del y term. Okay, let us do an integration of del v by del y term. Even there, when you do this integration, what will you get? So, when you do this integration for del v by del y, let us say you do it in y first, and you will get v at minus h minus of v at plus h. Okay, so
along with dy.
huh?
U not along with dy, the second term, half to half.
Yeah, u naught is 1, no, when we non dimensionalized. All of these are non dimensional. So del v by del y dx dy. So again, for x we have 0 to L, for for y we have minus half to plus half. So we have v at half minus v at minus half, this being integrated from dx. So what we get when we combine these is that minus h to h u of x equal to L dy minus 1 plus 0 to L v of half minus v of minus half dx equals 0. Now what I am going to do is I am going to, so of course this v of half and v of minus half, these are functions of x as well. Okay, let's not lose that from our sight, that we have done a partial integration here only in y. So these are functions of x. Okay, so just to, and this is again, this is a function of y. Let's not forget that. So I can take L to be general any x, and I can take a limit of h going to infinity here. Okay, so take limit of h going to infinity and L to be any x. Okay, any x location. What will you get? Maybe take x naught so you don't confuse it with the integration sign. So what will we get? Minus infinity to infinity u x naught y dy, we'll take 1 on that side, equals 1 minus 0 to x naught v of x comma half minus v of x minus half, x comma minus half, sorry, dx. If the flow is symmetric, what can you say about v of x comma half and v of x comma minus half? What is the relation between these two? If the flow is symmetric, what is the relation between these two? Minus of it. So 2 times v of x comma half, right? Whatever you have v here, you have the negative of v there. So when you're subtracting, you have 2 times v of x comma minus half, or 2 times minus of v, whatever. So this is, so v of x minus half is actually minus of this. So this quantity is so 2 times v of x comma half dx. Now the question is, what is v of x comma half going to be? Actually, hold on, sorry, my bad. This was minus h to h. So this should have been minus h or h to minus h. Okay, that's what our control volume is. This is not from half, it's from h. And we have taken the limit of h tends to infinity. So technically this is far away from the jet. Now what can we say about this quantity? What can we say about this v of x comma infinity dx integration from 0 to x naught? Hmm? What can we say about this quantity? Is this going to be 0? Is this going to be 0? Is this going to be positive? Is this going to be negative? What? Hmm? So first of all, one thing that we can agree is that v is small compared to the x direction velocity. Okay, v is small compared to x direction velocity. But notice that I am integrating this small quantity over a large distance also. The 0 to x naught, this x naught was L, and we took the control volume such that this x equal to L, we were sufficiently far away from the inlet or the orifice, outlet or the orifice. So, I am integrating a small quantity over a large distance. Okay. So, in general you cannot just arbitrarily say that, oh, v is small, so this integration is small. Okay, you cannot just arbitrarily say that the v quantity is small, so this integration is small. Now, okay, we are saying that it is not small, it is not infinitesimal, it is not 0. So, let us talk about its sign. Is it going to be positive or negative? What do you think? Is this integration going to be positive or negative? So, I will leave here and then you guys can think about it, and there is a concept of flow entrainment that you can look at, based on which you can guess what is the sign going to be, and the concept goes something like this. You have flow of some velocity coming outside, it is going to accelerate the flow, it is going to accelerate the flow in its boundaries at other y locations. Okay, and what it does is it basically sucks in the other fluid, the outside atmospheric fluid also into the jet. So, there is an entrainment, there is an overall entrainment inside this jet, and we are going to derive what this entrainment is equal to. Okay, but for this case what I want you to notice is that due to flow entrainment you cannot say that mass flow rate or volume flow rate coming out of this is equal to volume flow rate going into here. They are not equal, because there is some flow that is sucked from the boundaries of this control volume as well. Okay, and so we will see how this can be applied in equations for jets.